I'll talk about relatively old question for topological insulators, the bulk edge correspondence. We already heard one talk yesterday about this by Alexei. I'll give yet another perspective via Fredholm theory, which started when I was still in Zurich. So with Jean-Michel Graf, we first thought of this idea. And during a summer project in Columbia University with 4 other students, we developed this a little bit further. All right, so this does not seem to work. Okay, maybe now. Yes. So what is the main message of my talk, or what is the bulk edge correspondence at all? So we have an infinite space topological insulator that is specified by a Hamiltonian edge. That is always the starting point. So the edge and the bulk do not stand on equal footing. The bulk is somehow more fundamental. And out of the bulk, we can either start to calculate bulk invariance. And in order to do that, we have to flatten the Hamiltonian. So it entails solving the eigensystem and eventually getting to an operator, the flat Hamiltonian, which I denote by the sign function on edge, that is unitary and self-adjoint. So because we assume it's an insulator, so it has a spectral gap without loss of generality about 0, then eventually the spectrum will be just -1 and +1. And it turns out that all topological invariants for the bulk go through calculating this flat Hamiltonian, which is also equivalent to the Fermi projection in the spectral gap regime. And so you need to go through this step to calculate bulk topological invariance. On the other hand, you can say, well, I want the edge picture. And if you want the edge picture, then you have to truncate your Hamiltonian to the half-infinite space. Let me denote this truncation process by blackboard lambda. And for example, in 2 dimensions here, you see an example that it's just the upper half plane. And of course, you have to truncate if you want to calculate edge invariance. And so the bulk edge duality or correspondence says that, that starting from the same point on the top, the same bulk Hamiltonian, and putting any kind of boundary conditions for the truncation on the edge, these 2 invariants should be the same. This is a very general principle for all topological insulators. And my perspective today that I want to present is via Fredholm theory, which essentially says that these 2 procedures of truncating to half space or flattening in energy commute. At least, I mean, of course, they don't really commute, but they commute when you calculate indices. So this is not a very general proof. It has been proven for spectral gap topological insulators. I don't really know how to extend it to mobility gap strongly disordered topological insulators. For that, one needs other tools. And it also works right now in the tight binding regime. If you want the continuum, then together with Michael Weinstein, we did another separate study that asks about the difference between continuum and tight binding topology. Although in principle, I don't see an a priori reason why this type of proof should also not work in the continuum. You just need to regularize your objects. All right, so what do I want to do today? I want to first study this one-dimensional chiral example and show you how this principle of commutation, of truncation and flattening work in this simplest topological insulator. This is this green example. Then this will lead me to talk a little bit about Fredholm theory. And as much as time will permit, I'll talk about the 2-dimensional manifestation of this bulk edge correspondence perspective. Which is a little bit more complicated, but all right, so the bulk edge proof that I present here, it's not new. It goes back, as was said yesterday, to 1993, and it became more and more general, and this proof is not even the most general. So I'm just saying it's some, I think, good balance between generality and shortness. If you really write down the proofs, then can be just a couple of pages. And also there is no reason a priori why that perspective should not work for the entire table, although I did not work that out. I only worked the cells that are marked here. I guess really the most interesting thing that came out of it is this Z2 proof that is really much shorter, and I think this really shows the power of this tool. All right, so the chiral 1D example is a chain where you have, is a one-dimensional chain where you have two species of sites, let's say the balls and the squares. One is a plus chirality, the other is minus chirality. Here chirality is just a formal name for now. And you say that the Hamiltonian is chiral if it doesn't have diagonal elements in this chirality basis. And so in this block form, it should be off diagonal. So that means it should be written like that. It should be written with an operator S that takes you from positive chirality to negative chirality, and S does not need to be self-adjoint. No, you do not need any translation invariance. This is just in real space. I mean, you can take, for example, the shift operator, then it is translation invariance, just e to the ik, and you could work in k-space. But this framework does not need k-space. But if you do go to k-space for the shift operator, then you immediately see you have a winding number. It has winding -1 or 1. And that's what we recover here as well. So you have the chirality operator that is plus on the positive sides and minus on the negative sides. And having this off-diagonal form means that you have this anti-commutation relation, which in particular means that the spectrum of the Hamiltonian is symmetric about 0. So we should put the Fermi energy at 0. And so the spectral gap regime means that 0 is not in the spectrum. And so the process of flattening can be thought of as looking at the Hamiltonian and dividing by the absolute value inverse, if you think about it with the functional calculus. And so if your spectrum looked like so beforehand, symmetric about 0, then afterwards it should be just two infinitely degenerate points plus 1 minus 1. And then physicists tell us that we should define the bulk index as some sort of chiral polarization. So it is a trace formula, the trace in real space, involving the chiral symmetry operator, or the flat Hamiltonian, and then a commutator of the flat Hamiltonian with lambda being the projection onto the right-hand side of space. And why this commutator? Because if you did have translation invariance and you went to k-space, then commutator with lambda is morally equivalent to derivative with respect to k. So it is some sort of polarization. Okay, and if you work a little bit and you just plug in what these things actually mean, then you see after a few lines that this is equal to the trace of u star lambda u commutator. What is u? U is the subblock of the flat Hamiltonian. So you can identify u as the polar part in the polar decomposition of S. This is how the polar part is defined. Again, it makes sense to write it like that because S is invertible, because we are assuming we have a spectral gap. So in particular, u is unitary, and lambda is a projection. So when you open the commutator, you see you have the trace of a difference of two projections. This is an object that has been studied before by Avron, Zeiler, Simon, and it can be shown that this is actually equal to what is known as a Fredholm index of lambda u lambda plus lambda perp. You should think of this formula as a truncation to the right-hand side of the flat Hamiltonian, or more specifically, a subblock of the flat Hamiltonian. And just for notational brevity, let me denote this lambda u plus lambda perp as this blackboard lambda u, just the truncation to the right-hand side. So, okay, what is Fredholm index at all? If you're not familiar, let me spend a few slides. So an operator is called Fredholm on a Hilbert space if it has a finite dimensional kernel and kernel of the adjoint, and moreover if its range is closed, which means, roughly speaking, that if you consider the inverse on the complement of its kernel, which you should be able to define, then that inverse is a bounded operator. That's the equation you see here. So this roughly tells you that the kernel measures deviation from injectivity, the kernel of the adjoint measures deviation from surjectivity. So it means that if we ask for the difference of the two dimensions, we sort of measure how much this operator is not invertible. And it should be Fredholm if it's not invertible up to something finite dimensional. So that's what we're interested in here. And it is manifestly integer valued. So what is very important for us, there are many properties of Fredholm operators, but what I want to focus on is the fact that this index is stable under compact perturbations and also under norm continuous perturbations. So what are some examples? The identity operator is invertible, and we expect its index to be 0, which it is indeed. The zero operator is of course not invertible, and on any infinite dimensional Hilbert space, it's not going to be Fredholm. An interesting example, perhaps an archetypical example, is the right shift operator. If you consider this on little L2 of n, the half chain, then it is the operator that just shifts your wave function, everything to the right, collectively. And on the bilateral chain, it does the same thing. So on the bilateral chain, it's going to be invertible. You don't lose anything. But on the half-infinite chain, the adjoint is going to kill one state. It's going to shift to the left and kill the first side. And so the kernel of the adjoint will be one-dimensional, and that's why you have index -1. The inverse of the position operator on little L2 of n is not Fredholm, although it has no kernel and it's self-adjoint, so also the adjoint has no kernel, because the inverse, which is just x, is not bounded. And the operator that we are interested in for our chiral one-dimensional chain, this truncation of the flat subblock of the Hamiltonian, that is indeed Fredholm. This follows by locality and the fact that the Hamiltonian has a gap. All right. Now let's consider the half-infinite geometry. So you have to make a truncation in your chain somewhere, and you can pick any boundary conditions that you want. Now, because chirality commutes with the position operator, then having the truncation means that the edge Hamiltonian is going to preserve this off-diagonal structure, and so S hat, which is the truncation of S. So everything sort of is compatible with each other. And because S was invertible, and of course it's Fredholm, but its index is 0, so that's not interesting. But once you ask whether the truncated S is Fredholm, then the answer is indeed yes, because again, by locality, you can see that the difference between S and the direct sum of the left-hand side and the right-hand side of S, where you just cancel the coupling between them, is going to be a compact operator. So if you change by compact, you don't change the Fredholm property. And so for the edge, the index should be just the index of this truncated S. And so here we come to the first manifestation of this principle of bulk edge correspondence, which is the question whether the Fredholm index of these two operators is equal. And my campaign is sort of to say, once you get to that level, to ask whether the index of two Fredholm operators is equal, then the rest of the proof is very, very easy. That is my message. So why is that? We see that the bulk is the truncation of the flat subblock of the Hamiltonian. The edge is just the truncation of the Hamiltonian itself. You haven't done anything to it. It is the case that the index of an operator is the index of a polar part of an operator, so you can put polar part here for free, and then the question is whether truncation of polar part is equal to polar part of truncation as far as the Fredholm index can gauge. The answer is yes. Why? Because you can make a deformation between S and its flat version, and then you can truncate this deformation. And if you can make sure, and indeed you can, that the truncation stays Fredholm for the entire duration of the deformation, then you have, by the constancy of the Fredholm index, that the two endpoints also agree, and so that is the bulk edge correspondence. Let's go on as much as I have time for the two-dimensional case. So in the two-dimensional case, we again assume that the Hamiltonian is gap. That is what it means to be an insulator in the spectral gap regime. And so without loss of generality, we put the filling level at 0. Otherwise, you shift by a constant. And the main object for the bulk is the Fermi projection. The Fermi projection is related to the flat Hamiltonian like this in the spectral gap regime. So again, the bulk is determined by the flat Hamiltonian. Let us also define U. This is now another U, which is the polar part of the position operator in 2 dimensions. This is related to a flux insertion at the origin, which implements an electric field. Then it turns out, it's a non-trivial fact, that PUP plus P-perp is a Fredholm operator. This is because the Hamiltonian is local and has a gap. Okay. That's just a fact, but okay, what do we do in the integer quantum Hall case where you don't have time reversal invariance? Then you know that the invariant should be the Hall conductivity, which is given by the Kubo formula. So Kubo formula, people usually use the Berry curvature integral in momentum space. However, I do not want to assume translation invariance, so I use this formula right here, which is equivalent when you do have translation invariance. So it's a double commutator. Lambda 1 and lambda 2 are projections either to the right-hand side of space or to the upper half space. And again, in K space, this would be derivative with respect to K1 and K2. So you sort of see the shadow of this Berry curvature. And after some work, you can see that this formula, which is not manifestly an integer, is equal to the Fredholm index of PUP plus P-perp. So this was first described by Jean Bélissard and collaborators some decades ago. And so it is manifestly an integer. In the time reversal invariant case, you need the time reversal operator, which squares to -1 for fermions. It is anti-unitary, anti-linear operator, and it should better commute with the position operator because it should act locally in space. Hamiltonian is time reversal invariant if it commutes with time reversal, and that immediately implies also that the Fermi projection commutes by the functional calculus. And so you can see that U can be written as the time reversal operator, but you need to put the adjoint because you have the complex I here, and you need to put the minus because it squares to -1. P, however, just commutes with time reversal, so you don't have the adjoint, and it's anyway self-adjoint. So our main Fredholm operator, this PUP plus P-perp, obeys this algebraic relation. This algebraic relation in terms, let me not get into this calculation, but it implies when you plug in the algebraic relation and use a logarithmic rule for the Fredholm index, that you actually, the bulk index is equal to the bulk index of the adjoint of this PUP plus P-perp, but the index of the adjoint is equal to minus the index, and so that index is always 0. Let me speed up a little bit. So anyway, for such operators that obey this constraint, one defines half the Fredholm index, which is a mod 2 Z2 invariant. And that is, again, another theory that is derived from Fredholm theory. Let me not get into that. But just in the time reversal invariant case, you define this half index of PUP plus P-perp, which is the Foucault-Milly index. And so, as my time is up, I guess I should conclude. But it turns out that in the edge picture, you again can write the whole conductivity as a Fredholm index. And by a work of Kellendon, Krichter, and Schulz-Baldes, this is also manifestly an integer. And so again, the question of bulk edge correspondence, either with or without time reversal invariance, reduces to whether the index of two Fredholm operators agree. And again, when you work out the equations, it turns out that it reduces to the question whether to flatten the Hamiltonian or truncate it commute on the index. And in this two-dimensional case, whether you have or don't have time reversal invariance, the answer is yes. And so you find the bulk edge correspondence also in these two cases, which are somewhat more challenging than the one-dimensional case. Thank you.